Okay, good evening, everyone. Today we are very happy to invite Dr. Armand Demirs to give an invited talk on underwater communications and networking. Dr. Demirs is a research assistant professor in the Department of Electrical and Computer Engineering at Northeastern University. He's also a member of the Institute for the Wireless Internet of Things at NU. Dr. Demirs received his PhD in Electrical and Computer Engineering from Northeastern University in 2017. Previously, he received his master's degree in electrical engineering from University at Buffalo, and his bachelor's degree in electrical and electronics engineering from Bilkent University, Turkey, in 2014 and 2009, respectively. His current research interests are in Internet of Things and 5G networks, underwater communications and networks, Internet of Medical Things, unmanned area and underwater vehicle networking. In 2014, Dr. Demirs was the winner of the NUTAC Software-Defined Radio Academic US National Contest. He received the Best Paper Awards of EE701 2015 and 2016, HB WildMom 2019, ACM WinTech 2019. He serves as an associate editor for the HB Access. Dr. Demirs is also the co-founder and director of R&D of Bionaut Sonar. Amir, please take it away, please.
Thank you very much, Guan, and thank you for inviting me. Let me first share my screen. Please confirm if you can see my screen.
Yes.
Okay. So I'm very happy to be here, even it's virtually. I mean, I hope I can be back at some point and visit Buffalo. I mean, I studied there 3 years. And then in my presentation, you will see quite a bit of Buffalo pictures and Buffalo sites, actually, because we have done quite a bit of work there as well in underwater when I was a master's student and started my PhD at the University of Buffalo. So once again, please feel free to stop me at any time to ask questions if there's any, anything that you would like me to elaborate a little bit more. Feel free to stop me anytime. And I guess without further ado, I will start. I have quite a bit of stuff, so I guess I don't want to lose much time and I can talk a little bit about that. So today, as Gwen presented, I will talk about underwater communications and networking. And then I would like to start, I basically titled my talk as like Toward the Internet of Underwater Things, a roadmap. Basically, I just want to start with describing what is underwater communication looks like. Why do we need that? What are the challenges first? And I would like to give you a little bit of the state of the art. Then I would like to share a little bit about, what is our vision, what was our roadmap, and then what were the milestone works that we have done to basically serve this vision that we have. And I will try to give you a few future remarks and future points that I think I personally think that will be useful for people interested in this topic and in this kind of research. And I hope at the end of this talk, you will have a good idea of what is underwater communications, underwater networking, and then where it's going. And I hope I can create some interest towards that topic as well. So without further ado, let me start my slides here. So as you can imagine, first question that you will ask yourself, okay, why do we need underwater? Why do we need to make underwater networks the citizens of the internet? I mean, do we need Wi-Fi internet? So I will show you a short video that actually back in 2013, we did a small video with a crew from CNN about why do we need underwater communications. So there's some spoiler alert about my, I will give you some spoilers in this video, but I guess it's good to always see how these things looks like in real world to begin first to give you the interest. So let me start this video. Can you hear it, the video?
These days, you may find wireless and Some of the most on the planet light, even in space, where you won't find it, at least not yet, deep underwater.
These are devices that can communicate underwater wirelessly.
Tommaso Melodia and University of Buffalo researchers developed technology they say will create a deep-sea internet, an idea initially fodder for late-night laughs.
A Wi-Fi network that can work underwater. Yeah, while Time Warner is trying to develop a Wi-Fi network that can work.
Of course, Fallon means Time Warner cable. Regardless, to Melodia, it's no laughing matter. It's been 8 years of hard work. Melodia hopes the technology will improve tsunami detection, natural gas exploration, pollution monitoring, and security surveillance. But will it work?
And how deep?
We went out to Lake Erie with his research team to test the science behind it.
When you communicate wirelessly in air, you do that through electromagnetic waves. When you communicate wirelessly in water, you do that through acoustic waves, basically sound.
It sounds a bit like how dolphins communicate. They use sound waves. These modems will use the same techniques to talk to each other.
He's trying to communicate to this guy.
Modems transmitting data from underwater to a modem on the surface, then to a laptop or cell phone anywhere in the world. Did you give them names?
We did actually for a specific experiment in which we have one of the yellow spheres called Alice that wants to communicate with Bob.
And it's into the water. So what happens now?
So the Alice will send a message from the underwater, and Bob will transfer this data to the internet.
After a few moments, a message. First via laptop.
Welcome CNN.
Then the mobile.
This is the message I was waiting for. So when everything works, we're like kind of, woo, that's it. We got it.
Today, Lake Erie. Soon, the hope the internet will finally go where no internet has gone before. For Out Front, Jason Carroll, CNN, Buffalo.
As you can see, it was one of the, it was, I guess, first year of my PhD and master's that I started, and it was the experiments that we were doing in the Lake Erie in Buffalo. And there's quite a bit of spoiler about why do we need internet in underwater and what could be the applications. But I guess this is a good motivation to see what is the real world looks like. And I will go a little bit deeper, what are the underwater networks? Why do we need underwater networks? Today, underwater networks will becoming an enabler for many different applications. There is quite a bit of interest in oil and gas industry for equipment monitoring. If you remember that BP incident back in, I guess, 2008 in Gulf, that is basically, there was a failure of a valve that is costing a disaster, and it, I guess, costed $90 billion worth of basically damage to the environment. So this is becoming something super critical to monitor these valves, to monitor these oil and gas drill fields. Another application is that today, especially in the US, there's more and more fisheries. There are more, as they call it, precise fishing. There are lobster cages. So there's quite a bit of applications in there as well. You can just imagine like a clever, intelligent cage. For example, today, if you want to catch a lobster, you set up cages all around the sea, and you're just going manually and checking them one by one if there is a lobster inside. So if you can imagine it, if there is a sensor inside that can tell you there's a lobster in that size, it's worth to catch it. It's basically, you can avoid all these things by using an underwater network system. And there's quite a bit of interest in military as well. As you can imagine, there's always a lot of applications in military for underwater networks. There can be underwater surveillance, that can be port securities, that can be diver communications, and that can be also autonomous under vehicles. That can be basically autonomous submarines. That can be similar to what's happening in drones in air today. There will be a lot of drones in underwater that will be operating in the future. So as you can see, there are a lot of different applications. And as the applications increases, the system needs are also evolving and becoming increasingly complex and diverse. So you need more work, you need more capable systems, you need more sophisticated networks to be able to address all these needs that is required from different applications. So let's look, what are the options that we can do wireless communication underwater? There are three main ways that people were studying. Actually, there's one more that I failed to mention here, is basically magnetic induction. Actually has been heavily studied by a UB professor as well, Ji-sun. It's another technique that is not as common as these ones, but the most common one that was, as you can think of, is RF waves, electromagnetic waves. Basically, it's whatever we are using in the whole wireless communication that is in the air, in terrestrial networks. But in underwater, because it's an aqueous medium, the water conducts the electricity. So either you have to be using very low frequencies, and the low frequencies I'm talking about 30 to 300 hertz. Then it will require quite large antennas, because as you know, the frequency and the antenna size has a reverse ratio. So smaller the frequency that you're using, you need larger antennas. So for a 300 hertz frequency, I guess you need a kilometer long antenna. So it's quite costly to have such things. And then you need quite a bit of transmission power, because as I was telling, everything is conducting in underwater. The other ways that people were looking is to use optical waves. Optical waves mean mostly we're using like high precision laser beams. As you can imagine, when you have a laser beam that is inside the water, there's quite a bit of scattering, because even you don't see it with the eye, there's quite a lot of different particles that is floating in different parts of the water in the sea. So there's some good examples of optical waves. There's also some other work that is focusing on visible light communication. So not only laser, but also some other part of the light that is visible, that's blue actually, which is proven to be the best frequency of the visible lights that can propagate in underwater. But most these are very short distance communications. So the most common used way of establishing wireless communication in underwater is actually acoustic waves. That has been used quite a while. From that video, as you have seen, there's dolphins and whales are already using it. So nature has already found the best way, probably, to communicate, the most efficient way, let's say, not the best, but. So there was quite a bit of different applications in the past, like sonar systems has been used heavily in since World War II. But they were mostly focusing on low data rate, very long distance communications, and they were looking for something very secure. So they were just sending some distress signals, like few bits of information. And there's a good reason why the data rates were so low. So I will come to that, and I will show you what the underwater acoustic channel looks like. It's quite different from an RF channel, actually. First of all, you're using sound waves. So sound waves in water has 1,500 meters per second speed. So which is compared to a speed of light, which is used in RF. That's orders of magnitude slower. It's basically, that is really, really reducing the network throughput. You always have a delay. So you can imagine, if you want to go a kilometer, you will have a 1 second delay in your signal inherently from the physics. There is quite a bit of multipath effect. As if you're in a small room, you have reflections from all over the place. There are always three main reflections that you will see. There is surface reflections, there is a direct path, and there is a bottom reflection. And if there is different type of environments, different type of bottoms, or like different type of surfaces, you will get even more a severe multipath effect. And multipath effect creates a severe intersymbol interference. And it's basically complexing the receiver design in order to resolve that multipath effect. There is quite a bit of Doppler effect. Doppler effect, as you know, it's basically created due to the movement. There's quite a bit of movement, nothing stable in underwater. So if you put a modem underwater, everything moves. The water itself is moving. There is drifts, there is different type of waves coming and back and forth inside the water. So all the waves that is going through that medium mechanically has a Doppler effect that is inherently added on top of that. So this is one of the quite challenging problems that researchers were trying to address that in the past 20, 30 years. Looking a little bit deeper, what are the other challenges and what actually the main factors that is dictating the bandwidth usage in underwater, there are two effects. There's the noise and the transmission loss. As you can imagine, there's noise and transmission loss in RF waves, in terrestrial networks, but noise in underwater is quite different compared to an RF signal. So there is different type of noises that exist in underwater places, in underwater channels, in underwater acoustic channels actually, specifically in different frequencies. So in the lower frequencies, if you look at it like up to 1 kilohertz or 10 kilohertz, you will see noises that is coming from shipping. There is noise from turbulence. There's noise from wind. So these noises that actually we can hear. So if if you're in the sea, if you dive with your ears, you can hear some of those noises. It's quite noisy actually down there if you try to listen with your own ears. And if you try to go higher in the frequencies, like if you try to go above 100 kilohertz, there is something called thermal noise. That's coming basically mostly from how mechanical waves are getting attenuated in the sea. So it's kind of creating a bounded bandwidth between high and low frequencies, and it's basically becoming a very limited bandwidth system. If you look into the transmission loss, it's not quite helping as well. It's on the right-hand side, you can see there is actually a logarithmic loss absorption on the x-axis, and there's the frequency on the in the x-axis, and there's the absorption on the y-axis, and you can see that it's basically exponentially increasing if you go higher in the frequency. So by 100 kilohertz, you get almost 10 times more absorption than what you're getting in 1 kilohertz. So this is quite limiting. If you look into the combined effect of these two things, you will see that in 50 kilometers, if you try to get a 3 dB bandwidth, actually you will see that you have only few kilohertz bandwidth. So few kilohertz bandwidth, compared to what we're using everyday Wi-Fi, that has in the megahertz is quite small. I mean, in Wi-Fi we're using 20 or 10 megahertz for just connecting and then streaming a video from Netflix. That's what we're using. So 1 kilohertz is quite small compared to that. If you go lower in the if you go lower in the smaller in the distances, you can see that it's actually getting a little bit improved. You can get less loss from transmission loss and noise, but it's still quite limited. So you will never get a quite good 3 dB flat channel in the water, unfortunately. On top of that, there is some other unique characteristics of the acoustic channel. There is something called stratification. So these mechanical waves are waves that are, I always say they're lazy. So these waves are always trying to bend towards where the speed of light is slow. So as you can imagine, as you can see here, the speed profile of different depths are different. So that's another fact here from the physics of the water. So if you go and look at the different depths, you will see that the speed of acoustic waves are not always 1500 meters per second. It's actually changing. It's getting slower. It's getting faster. And these are happening due to the minerals there. There's the chemistry. There is the temperature of the sea that's affecting all these things. So there's different speed profiles for every type of environment, and you get bathymetric data. They do measurements to understand that. But what this creates shadow zones. So you're here, for example, you're transmitting a signal. You're basically imagining that you're propagating everywhere. So you were expecting that if you're here or somewhere here, you will be able to receive it, because obviously, if you're in RF domain, it will come to you if there is no blockage in between. So there is no physical blockage. It's an open channel. Probably you can even see this if you look at it. But the acoustic waves, you cannot get them because they're bended towards where the speed of light, the speed of acoustic waves are slower. So it creates that shadow zones. And this is a quite interesting problem that I guess don't exist in many other mediums. I mean, there's also challenges. It's, everything is moving, everything is prone to failure, like corrosion, falling, because there's salty water in most cases. And also, transmit energies are quite high compared to RF domain. It's actually 100 times higher than RF domain. The reason behind that is that because we are using acoustic signals and mechanical waves, there is always a conversion loss. So you're converting an electrical signal by using as we call transducers for creating, projecting that sound or mechanical waves, or receiving that mechanical waves backwards, you're losing up to, I mean, I guess the best case scenario is 70% you can get. So you always, at least you're using 30% of your energy when you're transmitting. So you need much more energy in order to be able to communicate in underwater. And those devices are, they're always having a battery powered devices. There's always that limitation. It's very hard to recharge their batteries because they're somewhere in the sea, deep down in the ocean. It's very hard to retrieve them and charge their batteries. So these are quite operational challenges that you can imagine. So a brief overview of that is basically, as I was telling, there's quite a bit of channel effects that I mentioned earlier. As I was telling, there's also quite a dependency on where you're deploying. So the oceans are different, lakes are different, rivers are different. So everything is temporally and spatially varying, meaning that it's changing from time to time, it's changing from place to place. So there is no one system that can work everywhere with some capacity. So it's always, you need systems that can adapt themselves. You need systems and architectures that can be reconfigurable to be able to satisfy these environmental and applicational needs. So looking at it, today's technology, what are the limitations? Why we're not, having really internet and under, why we don't have that already? I guess there's three pillars here. There's the modems, there's the network abstractions that we're missing, and there's the flexibility and reconfigurable that I was mentioning that we're missing. So if you look into the modems, today modems are dependent on proprietary architectures. So they're like fixed chips, fixed boards, they have proprietary protocols. So everything is very limited. You cannot change them, you cannot evolve them over time. So you need to redesign them once and for all in order to get something else. They're also, as I was telling you at the beginning, they were always designed for lower data rates because the Navy was needing lower data rates, military was needing lower data rates. And the reason behind that is they were aiming to reach very long distances, and they were just aiming to send few bits of data. So today, if you go out there and try to buy a modem, I guess the best that you can buy is around 60 kilobits per second. But most of the time, you will get a modem that can send few hundreds of bits per second. So this is not good enough to be able to do video streaming or some type of sophisticated data transfer. It's very limiting, actually. And those devices that's out there, because they're not vastly, they're not very popular. So they're produced in, not in million units. They're used in tens or thousands of units. So it's very costly devices. And in the size-wise, they're pretty big because they weren't really caring about how hard to deploy them. So if you try to make a large deployment, it's quite prohibitive, actually, in terms of cost, time, sustainability. I guess in the video, you have seen these yellow big boxes. These are the underwater modems that we're trying to deploy. And deploying 10 of them manually is quite hard, as you can imagine. So we need some sort of easily deployed small modems, similar to what we have in our F domain. The network abstractions also are quite rudimentary in underwater domain. There is no support for IP architectures. There is no interoperability with standard internet. Most modems don't have any networking capability. So they're just working as like walkie-talkies. They just support point-to-point applications. They don't have any development abstractions. They don't really can implement any cross-layer control algorithms on top of that. And if you look at it, the architectures are pretty flat. So there's only one hub switch, and there's like all network is connected to that. So this is limiting the scalability of these networks quite a bit. And it's also limiting that bandwidth even further, limiting the speed, because you're trying to send all the data into one single hub that you have it there. And then if you lose that hub, or if you just lose one node that is inside that mesh creating that hub, it's quite prone to that failure. So here is, I guess, the message is that heterogeneity in heterogeneous networks is what we need to have, and that's the good part of it. And that's what is pretty common in RF networks. The other thing that we're missing, I mean, there's, as I was telling, the modems are quite inflexible. I mean, definitely we are not the first one seeing that. There was quite a bit of work, both in commercial and both in experimentals. Some of them were like having actually good results, but they were still some limited because they were still doing some assumptions. So even some commercial modems, they were saying, okay, you can actually, change some of the parameters of our proprietary protocols, but this is still hardware-centric design. So they still have closed software architectures. You're still unable to add new functionalities on them. If you look into the experimental and software-defined modems that is out there, that was been built, I guess, prior to our work, was they were having no network abstractions. So we were just like this analogy that's saying, like, imagine you're buying a CPU, a computer to your house, and there's no operating system on it. So you're just basically trying to operate them with bare bones, trying to, code them in the lowest level possible, which is making them very hard to operate. So our vision, in order to understand that, in order to make real Internet of Underwater Things, we call it CNET. It's actually been a project that has been going on, I guess, for the past 7 years. It's been funded by NSF, it's been funded by DARPA, it's been funded by different entities. Recently, we got a large NSF funding to build 50 of those modems with that vision, and we were basically hoping to deploy them by next year in the Boston Harbor here to build some sort of a semi-permanent testbed that people can use and people can do experiments even virtually, even from distance. They don't need to be there. So we're to get this in place. I guess it's going well. The thing is that the weather is not really helping us. We cannot do deployments all around here. As you can imagine, it's a similar issue in Buffalo as well. It's getting pretty cold this time of the year. So in this vision, we were having 3 main pillars that we think that is making this pretty unique, and then making it actually enabling that vision to support the Internet of Underwater Things. So the first one is to get reconfigurable and modular hardware. So in order to get to support different applications, different needs. The other thing is that to be able to support real-time adaptation algorithms, and also software-defined functionalities and abstractions, which is quite important to get a vision such as this. We have 3 main pieces that we were looking. There's underwater base stations. These you can imagine like Wi-Fi hotspots or like base stations that you have it in 4G, 5G network. We have it today. We were building a mobile high data rate frequency agile modems that can operate in different frequencies, that can support video streaming. They can adapt themselves. And then we have a little bit smaller devices, as we call it, Internet of Things platform, similar to what you have it like, low power Bluetooth, BLE, or like LoRa type of systems, Zigbee type of systems. These are like much smaller, much energy efficient, but low data rate. So it's basically designed for some basic sensing rather than just sending videos. To address that, I mean, there were quite a bit of work from our group, from also some other groups. But I guess we grouped them in three different aspects, as I was telling you: platforms, algorithms, control, and network architecture. So if you look into the new reconfigurable platforms, where we have started is that, okay, we're looking, can we get a software-defined radio to work as an underwater modem? Because the software-defined radio concept was there. There was already commercially available software-defined radios to do experiments. I guess that's the time that I'm talking about. This is in 2014, 2013. So we were already doing some software-defined radio work. And we were just imagining, can we just operate them in underwater as well? Can we just build software-defined physical layers? Can we do experiments with those? So with that motivation, we have done a work back in 2014 and called software-defined underwater acoustic modem with real-time physical layer adaptation capabilities. So we built a modem using a COTS commercially available software-defined platform. I guess you all heard probably of USRP in different presentations. I'm pretty sure Guan brought it up, that concept to you already throughout the classes. It's a software processing system. It gives you a front end, and it allows you to do different layer protocols implemented in software. So what we have done is that we have designed simple two different algorithms to showcase flexible adaptation of physical data parameters, or also doing a seamless switch between different signaling schemes. So we were switching between a multi-carrier communication method, which is OFDM, and then a spread spectrum communication protocol, which is direct spread spectrum. So it's pretty different, two different architectures that we were switching between. So I can show you how it looks like. It looks pretty, benchtop. It's not ready to be deployed in any way, as you can imagine. But this gives us quite a bit of insight how we can actually do experiments. I guess everyone from Buffalo knows where this is. It's Lake LaSalle. That's the lake that is in North Campus, next to the bookstore. So we have done quite a bit of experiments there. And it's a quite shallow lake. It is only 7 feet deep. So we put two modems by wires. As you can imagine, we wired the modems, the transducers here, the antennas of the modems, from the bare point here. And then they were like 200 meters apart from each other. And we were using 100 kilohertz bandwidth. And then we show actually quite impressive results. We were getting data rates around 100 kilobits per second, 200 kilobits per second. And that was at the time, it's quite impressive for us because we were having modems that was costing $30,000 and can do only 100 bits per second. That was a quite game changer in many ways. And we say, okay, we understand we can use a software-defined radio. There's quite a bit of resources. You have a computer. Can we minimize this? Can we just do something a little bit more towards Internet of Things platform? And on that source, we look into some resource constraint architectures like Tinsy. It's, pretty standard. You can buy one Tinsy. It's an Arduino-based chip. It's an ARM Cortex M4. It's pretty small. It's actually that chip that you can see here in the middle of the breadboard is quite small. And we built a small underwater modem out of this. These looks pretty chunky, but these are like evolution boards. So we didn't actually have a designated, PCB built for specific for that. But what we're having is that quite small chip that can operate as a underwater modem and can do actually quite good results. We tested them in different tanks. It was implementing a zero padded or orthogonal frequency division multiplexing. It was using a 100 kilohertz, 10 kilohertz bandwidth, and it was getting actually data rates up to 40 kilobits per second. In a tank, you get quite a bit of reflections from everywhere. It's one of the worst channels that you can find because the multi-path effects actually is much more emphasized due to all these closed environment. You can just imagine yourself in an empty room and then you're hearing your echoes when you're speaking. That's kind of what experiments in underwater. You get around, I guess, 200, 300 multi-path effects. So you get that much taps. So you need that much pilots in order to be resolved that much paths. It's quite challenging environment. But we were able to post tweets from that setup. We were doing some quite fancy work. And the nice thing about it is it was pretty small. So it was pretty energy efficient, can operate. It was pretty cheap. It's a $20 board and, some different eval boards that was probably the cost of the items were below $100, $200. So it was quite remarkable in our, in our perspective to have something like that. Then we started looking, okay, can we get this a little bit more sophisticated? Can we do actually some other things with it? Because that's the other pillar that we were looking. Can we do high data rate reconfigurable modems? And to do that, we actually adopt something called hybrid software hardware architecture. Because one of the other problems that we have noticed when we were doing the initial experiments, if you start getting a lot of bandwidth, you're seeing that your software cannot be able to process that much bandwidth data in the real time. So you're getting lagged. So in this first experiments that I was showing you with the USRP, we're using 200 kilohertz. And we're getting pretty large FFT sizes because you need quite small bandwidths in OFDM in order to be able to match the coherence bandwidth of the underwater channel. And this gives you FFT size of 8,192, so it's quite large. And when you start processing that much FFT, try to do that in a CPU, things are getting pretty slow and it's getting more delayed. Everything is getting slower. So at some point, nothing works because everything is lagged. It's becoming like a cloaked system, basically, that you're getting more data that you can process. So what we're looking is that, can we just do it in a way that we can, define it in software with the flexibility of the software, but can we just actually execute them in hardware? So in that way, can we get, good of the both camps? And that's the idea behind that hybrid software hardware architecture. So what we were doing is that we were building architectures that depend on system on chips, these Zinc system on chip systems, which have a processing system and a programmable logic. So it has a CPU, ARM Cortex A9, and an FPGA that is, so I guess, Vertex level capabilities on the same chip. And they can communicate with these high bandwidth AXI connections that can send data between two platforms quite instantly. So in that way, what we were doing is that we were putting everything processing sensitive into the intensive into the FPGA, which can do all the processing intensive functionalities without any problem. It can do it in real time almost, all the FFTs and everything. And we were just defining them by using our software, and we're reconfiguring that hardware by using software. And in that way, we actually can enable high data rates that can do megabits per second over short links. So we actually have some results that I will show you now, that we were doing like 1 megabits per second in quite short distances that we were hoping to extend, and we were actively working on that. Another good thing about this is basically we can also do spectrum agile systems with cognitive capabilities. So we can actually understand which frequencies are having high interference, having high noise. As you can see, noise is quite frequency dependent, so you can actually avoid some part of the frequency on the fly. You can do also interference alignment. You can do some sort of even security algorithms that you can avoid different type of interferences that is intended by jammers. And it also gives you a cross-layer controllable reconfigurable protocol stack. It's not only giving you a physical layer, but it gives you also a controllable full stack that can help you to do decisions using parameters from different layers. You can get a decision using the routing, medium access control, and physical layer combined. And in this way, you can give a cross-layer decision, which improves the system quite a lot, actually. If we go a little bit deeper, how we build it, and then, it's actually quite interesting parts of that is basically, we were also looking into getting different transducers to be built in the context of this project. So we were working with another colleague of ours here in Northeastern, Matteo Rinaldi, and they were saying that we can build actually better piezo circuits, because today we're dependent on piezo ceramics. So these are like ceramics that you charge them, you're driving them with electric circuits and creating mechanical waves, but just moving. And they were saying we can build like micro machine transducers. So they look like these ones, actually. I can zoom in here if you can see it better. So these are like micro machine PMATs, as they call it. And you can do quite a bit of different things if you have those effectively. So you can do massive MIMO, you can do beamforming, and you can get quite a bit of bandwidth from them. And actually, we did some experiments for intrabody. We were getting like video transmissions in very, very low distance, very small distances, because they weren't energy efficient here. They were still optimizing them, but it was quite promising as an alternative technology, as an antenna of these systems as well. So this is how the modem looks like. It was looking like I guess 2-3 years ago. So we were building in a way that has a modular architecture as well in hardware as well. So we're building, this is the Zinc SoC chip, and we have ADCs and DACs, and we have underneath that amplifiers. So if you want to use and operate in different frequencies, or if you want to improve something, you want to improve the analog to digital converter, you can change all these individual boards. You can just build a new one, and then you can just plug and play. These are standard connectors that you can change them pretty easily. So that's, we were calling it a stackable network, that you can change them. And can get you, also a hardware reconfigurability in a way that you can keep evolving and have the flexibility to operate with different front ends, different transducers, different frequency bands as well. So I will show you a little bit more on that. I mean, there's some results that we got it in tank and also in the sea. In the tank, as I was telling, we get actually quite large, like close to megabits per second data rates. In the sea, we have done also some short distance experiments, like 10 meters, and we were getting half a megabit, so 500 kilobits per second data rates with quite well beta rates. I mean, 10 to minus 3s, which you can get a good video streaming quality with kind of beta rate. So there was actually one more type of work that we were looking as well. I mean, apart from these pillars, we were also looking, can we actually use the standard phones as well, like our underwater modems? Because I mean, each phone has some sort of an acoustic interface. We have aux cables, we have microphones. So we were thinking, okay, can we just plug in a front end to an aux system of the computer, of a phone, of a standard phone? Can we just build an app that can act like a modem? And this is what we have named it as iSonar. It's basically transforming a smartphone into an acoustic software-defined radio that's basically running all the processing in software. And it's pretty similar to that IoT platform I showed you, can operate in tens of kilobits per second. We have done some tank experiments, and we're be able to do some messaging and sending some small files between different phones by just using that small front end, which is, in our opinion, is quite cool, because then you can jump into the water with that front end and to be able to still communicate underwater by using your own phone. So that can be a promising result. I guess with the technology improving phones as well, it's more waterproof. They have better casings. So in the future, that actually become something that we use it every day. That's we strongly believe in. And there's already some startups using similar ideas, putting things like iPads or like making like casings that has interfaces. So it's becoming something really, really interesting and useful. So this is pretty much reconfigurable platforms. I will also show you some of the recent photos of our platforms and recent videos at the end of this presentation, so you get an idea where it's actually kind of converted into what is becoming, it's evolving. And what we believe is still there is some future platform needs that we believe in the future. The underwater platforms will be completely autonomously frequency adapting themselves. There will be some cooperative relaying, interface alignment. There will be analog network coding implemented in these modems. There will be, I mean, at this point, yes, there is quite a bit of that, but there will be real-time partial reconfiguration of the modem that can change everything on the fly, which we are doing at this point up to an extent. There will be cognitive energy harvesting systems that can harvest energy from the noise and interference in the scene, so you don't need to change the batteries of these devices. And another important future platform that I guess that I really, really value is that one of the things that we're actively working is to get a multimodal platform. So these basically means that a platform that doesn't have only acoustic front ends, but have also optical front ends, have magnetic induction front ends, have RF front ends. So it's basically bringing everything into the picture, and then based on where you are and based on what environment you're operating, you can just use different front ends in different modalities. So you're always getting the best out of your system. You can think of it like, a system can talk many languages with different modalities. This will enable quite a bit of different applications for future underwater networks, we believe. If we go into the algorithms and control, network architectures for definitely. The network architectures, as I was telling, we were looking, okay, there's no IP compatibility. So in our initial work, we were looking, can we get some, a lightweight IP on top of these existing modems? That's the work that we were doing, and then we were able to get some IP. And the reason to get it, to make it a lighter version of that, because there was no data rates. I mean, these modems can do I guess, in a very good day, a few kilobits per second. So you need to lighten up the whole IP architecture. So we did quite a bit of ad hoc work here in order to get the standard IP to be work with these low data rate supporting modems. Then we see, okay, what kind of software framework that we would need in order to enable this network architectures. And we were looking into software-defined networking frameworks. I mean, that was actually where the CNET name comes from. So we were looking into a software-defined multi-layer functionalities running on a general purpose unit. It can be MCU, it can be an FPGA, it can be a GPU, it can be a combination of all of these things. And it's basically converting that unit into underwater acoustic network devices. And we were offering, a modular set of libraries that you can use, and you can basically reorganize them in order to create different physical layer communications. So you can basically adapt each layer's algorithm. And there's quite a bit of analogy here that I will bring it up, at the end of my talk. Is basically this is where all architectures in communications is going towards as well. I mean, the 4G, 5G networks were very, very monolithic proprietary. Now everything becomes software defined, open designs, modular, because we need those in order to get, fast innovation, collaboration, we need operational optimization, we need optimize experiences for users and the nodes that you're serving. So these are becoming actually an industry standard if you look at it into the different domains. And I strongly recommend you to follow, 5G and 6G standards, because it's actually kind of showcasing where the whole wireless communication kind of the ecosystem is converting towards. That's basically becoming more software centric, becoming more virtual, becoming more modular, and becoming more open design than what has to be, what used to be. So there's not going to be a proprietary monolithic systems state here. I mean, I guess used in 10 years from now. So there was also, as I was telling, the hardware configuration of things. So the hardware configuration means, implementing things on a FPGA and then can reconfigure and reprogram them in real time. So you get still the real timeness of the FPGA in terms of processing capabilities, but you can also reconfigure them. You can change the parameters, you can switch between different physical layers. Actually, there is something called partial reconfiguration that you can flash the bit files of the FPGA on the real time, and you can put different designs. So you can just put in completely new design on your FPGA while still operating and doing other physical layer communications. I can skip that. I guess this is quite detailed here. Another thing that we're looking, and actually had a pleasure to look with Guan as well. Guan was leading quite a bit of works here in the algorithms and control. So I will bring it up a bit of his work. So looking into the adaptive medium access control for underwater. So Guan was leading the effort to basically building a stochastic channel access for underwater acoustic networks, because as I was telling, the channel is spatially and temporally varying in terms of interference as well. There's always uncertainty. So building a modem, building an algorithm that's basically resolving a sum throughput maximization by getting the inputs of interference channel information and then your Q information, and then solving each node a sum throughput maximization algorithm in order to get the best medium access control based on this stochastic model is one of the things that I find pretty unique, and it's something very, very useful for a channel like underwater, that the delays are so high that the standard medium access control methods such as CSMA or like TDMA doesn't really work. So there's always quite a bit of value in that kind of innovative ideas. Another thing that we were looking is to how to do the adaptive physical layer. I already talked quite a bit of that, how we can change the physical layer and how this is affect. Actually, I would like to show why it's important and why it affects here in this experiment here, the experiment in Buffalo. So what we were doing is that here we were just changing the data rate basically by changing the modulation and depending on the SNR that we are operating at. So if you change, for example, your data rate and go with 10 kilobits per second instead of 25 kilobits per second, you were getting almost 0 beta rate. If you don't change it, you were getting 10 to minus 2 bit error rate. So you're actually can see that difference between being an operational modem or non being an operational modem is really, really depend on this adaptiveness in the physical layer. And another thing that I was telling you earlier is basically we were also showcasing that we can switch between OFDM and direct spectrum, which is quite unique as well, because in this way, actually, you can also enable something called bilingual or multilingual modems. One other thing, actually, I find it quite interesting to brought it up here, is basically there is no standards in underwater. There's no standard communication physical layers. There is nothing like Wi-Fi. There is no 4G. There is no Bluetooth. Basically, there's no commonly accepted physical layer that everyone uses. There is only one standard that has been set it up, I guess, 2-3 years ago by NATO. It's called Janus. So that's the only one that's kind of the baseline for all modems. So what it means is that if you get a modem from one company and then you get another modem from another one, they're not being able to operate with each other because they're just talking using different languages. They're using, one of them is using OFDM, the other one is using spectrum, the other one is using chirp-based communication, so you cannot make them communicate. So I find it pretty valuable if you have a modem that can switch between that and can operate between that. It will enable the heterogeneous networks that we're looking for. I mean, analogically, you can think of like you're trying to connect your Wi-Fi, and then if you have an iPhone, you can connect with an Apple Wi-Fi, and if you have a Google phone, you cannot connect to the Wi-Fi. So this is kind of the analogy that we have in underwater today. So that's what we're trying to break. That we're trying to build systems that can communicate with different vendors' phones and different vendors' communication devices. So this is why I believe it's quite important to have this. So I just want to go a little bit also, a food for thought part. As I was telling, I give you a little bit of spoiler. I couldn't stop myself earlier. And I was telling is the future control is software defined? Will the underwater modems also become complete software defined? I believe yes. And there's many good reasons. As I was telling, there's quite a bit of analogy in RF domain as well. There's quite a bit of advantages, but there's quite a bit of challenges to get this software-defined networking in underwater as well. We still don't have the backbone of infrastructured system. So if you look at it, the systems out there, there's the traditional SDN open flow. We don't have that high data rate, reliable communication link, which is Ethernet cable in a sense. We don't have that. So in underwater, what we're trying to do is that we're trying to build very complex hardware-dependent cross-layer programs for each modem. We're programming each modem. We're programming each underwater device, and this is becoming a really a burden for people to deploy this. So this is something that actually was invented and led by Guan, and I was very lucky to be part of this work. That we were looking into some unique and new techniques, how we can get the bridge between, how we can bridge the gap between software-defined networks and distributed network optimization control. And we were looking, okay, we need to provide network abstractions, hiding the lower layer protocol details. We were looking, okay, can we just hide the details of distributed implementation? So basically, we were looking some sort of underwater network operating system. So it's a network operating system to operate the whole network from a user perspective without knowing what is going on in the network itself. So you're just basically setting global, you're setting a global control problem with an abstraction, and then the network itself is solving the problem and then basically operated. I guess you have also listened one of my other colleagues' work, Lorenzo's work, which is an implementation of that in with drones, a kind of a different flavor version of that one. So this is actually something that I was very lucky, as I was telling you, with Guan on this. So it was something that is what we're doing with this work. We were getting a network abstraction that can be, you can think of like, okay, we would like to get the maximum throughput from that network. And what it was doing, we were getting a automatic network control problem decomposition. We were getting optimization algorithm generator, and then we're converting them into the programmable protocol stacks, which are all deployed in each modem. And each modem was operating in order to get that initial central problem that we have defined. And all these things were happening in RF domain in few seconds. So it's, imagine that you're doing that in underwater with all these things that we have to do today. If you can bring them into underwater, it's quite a bit of gap to bridge, which is, I believe, is going to be very, very, very important. One other thing before I get into the pictures, actually, here I will describe a little bit more what we're doing here. Is basically another thing that I believe will be important also is to also implement some of the AI and machine learning algorithms in underwater as well, because there's already been some work going on in RF domain, how to do AI in ML. And I believe in underwater, there's quite a bit of room for doing this, because can be done, blockage prediction, as I was studying, shadow zone prediction. There can be some beam alignments based on these machine learning algorithms. There can be some protocols identification, and you can also detect or identify or learn the adversarial and interference effects. So these are quite valuable, because in underwater transmission, in underwater acoustics specifically, the transmission and reception is very, very valuable, because it's very costly. It's 100 times more power, as I was telling, circling back to where I have started. You're spending 100 times more power, and everything that you're sending is going much slower. So you cannot just, have redundancy in order to do many things. So you need to be very, very careful how many times you're transmitting or what you're transmitting. So these, I guess, the AI algorithms will help us to do that decision much better, and will allow quite a bit of different applications in the future. So I would like to show you a few pictures and a video before I finalize my talk, and maybe take some questions if you have any. So this is the final version of our modem. So it's quite improved. It still have the same board, but this modem has been tested in the ocean so far in the Boston Harbor, and then I hope that we will be presenting the results quite soon, I guess, in one of the good venues. We have also been working on adapting these modems into standard ROVs to be able to get rid of the Ethernet, the tether cable. So this is a standard off-the-shelf blue ROV remote operating vehicle. As you can see, there is our modem here, and then it's integrated with the main computer of the ROV. So what we're hoping to get is that we're hoping to get a tetherless ROV that can go around with, we can remotely control it, and then being able to get the video and other sensor readings back in real time without too much of a delay. Because in order to operate an ROV like that, you need 500 meters, or 100 meters of cables, which, weighs quite a lot. It's very, very inflexible. It's very hard to deploy. So if you have a modem like that, to be able to operate that ROV, it's going to get quite a bit of flexibility, and you can do a lot of different things in underwater. Another thing that we have built throughout this project, we also built a buoy. We call it a smart buoy. We recently published that, in the Oceans Conference. It's basically something that is making a bridge between the underwater modem. So the modem is connected to that buoy with the Ethernet cable. And in this buoy, we have a high-speed Wi-Fi connection. We have a low power, energy efficient. I believe it was we tried different things. The Zigbee connection, that's basically for turning it on, turning it off the system, so you don't eat the whole battery. We have a new version with solar panels. So we were just using them as enablers of our test bed. So when we actually finally deploy that semi-permanent test bed that I was mentioning, that modems will be accessed through that buoy. So you can actually use our modems to deploy different architectures, different algorithms, and test them in a real environment. So I would like to show you a short video of how we are deploying these guys. So this is Boston Harbor. So it's taking quite a bit of time. As you can see, there's quite a bit of ropes here. So we're deploying the buoy. Let's skip a little bit here. and then the buoy follows by a modem that is basically wired completely. And then we're leaving this and going to the next one. So we deploy 3, 4 of them, and then we have our network ready to go. And then from the ship, we can do experiments. Actually, from anywhere we can do experiments. I mean, we were leaving a team in the lab, so we were deploying and we were doing experiments through using the standard remote connections, as you can imagine. So I guess with this small meme, I would like to finalize my talk. It's that a joke that O'Brien was making about wireless communications, that people can tweet, "I'm drowning," and that's actually one of the things that we're always making a joke. It's something like our "Hello world, I'm drowning." So I guess with this, I will finalize my talk, and I will be happy to, get any questions if you have any. Thank you both again for inviting me.
Thank you very much, Amir. I believe it's a great talk. I have been enjoying quite a lot. Even I have heard some of the part of your talk, but some are new to me.
That's great. That's great.